Hello again. So this is Structural Analysis and Design Made Fun and Easy. So this is part 2 of the 3-parter on structural concrete design to BS 8110, the beam sections. I've already done the first part of this video. It's a single span beam with small cantilever. So part 1 was analysis showing how to get the forces from the moments. And now I'm just going to do design of the section at the support. So this is a summary. This is where I worked out what the moments were, the reactions, cantilever moment, and there's the envelope for the moment diagram. So now, part C of the question is, check whether the steel reinforcement provided as shown in the figure is sufficient to withstand maximum design support moment. So that's the hogging moment, which is breaking it at the top. So it's going to break the top of it. So I've just done a diagram of the section that was given in the question. It shows three bars at the top. So these become the tension bars because we've got tension at the top of the section. So here I've just done, this is a little kind of indicative stress diagram. So we've got compression at the bottom, which I've just shown in blue, and tension at the top. So this diagram isn't to scale or anything, but it's just to give you the idea that basically it's tension at the top and compression at the bottom. So we first of all we need to find out what the effective depth is, and the effective depth is the distance from the top of the section, which is now the bottom, to the center of the tension steel. Now the tension steel is going to be in the top. So I've just drawn, this diagram's not perfect, but it just shows roughly that the tension bars, longitudinal tension bars, they're going to be within the concrete but within the links. So the effective depth is equal to the depth of the whole section minus C, which is the cover to the links, minus the link diameter, minus half of the tension bar diameter. So that obviously gives you the center of the bar, which is the effective depth. So I've just written it again there. D is the depth from the top of the section to the center of the bottom bars, but note in this case the bottom bars are the top. So the effective depth of the steel tension reinforcement is D minus C minus link diameter minus TT over 2. So that's 350 minus 30 minus 10 minus 16 over 2, which is 302 millimeters squared. So it's given in the question that you have 3 T16 bars at the top. So the area provided, it's saying check that the the tension reinforcement provided is okay. So you need to find out the area of 3 T16. So usually you would use the charts if you're in the design office. Use the charts. The areas, but I'm just going to do it the long way so you can see how it's, if you ever get stuck or you wanted to know how it's done, you just do pi r squared basically, so it's simple. The area of 1 T16 is pi times r squared, which is 3.142 times 16 over 8 squared. So that's 16 divided by 8 is 2 squared. And that gives you 201 millimeters squared. So that's 3.142 pi r squared pi times 8 times 8, pi times 64 basically. That should be divided by 2. So the area of 1T16 is 3.142 times 16 over 2 squared. It's 3.142 times 64, which is 201 millimeters squared. The AS provided is therefore 3 times 201 millimeters is 603 millimeters squared. So we've already worked out that the effective depth is 302. So now we just take the equation from BS 8110. We need to find the usage factor, which is the K. K is equal to M divided by B, which is the width of the section, effective depth squared times FCU. So that's equal to, I worked out the moment in the other video, 60 kilonewton meters. So 60 times 10 to the power of 6, and then divide that by B, which is 300, divided by 302 squared, which is D, effective depth squared, and FCU, 30 newtons per millimeter squared. That gives you 0.0731. Now, as then that confirms that's less than 0.156. That means that no compression reinforcement required. Which confirms what it says in the question. So the next bit, we need to find what the lever arm is, Z. So Z divided by D, the standard equation in BS 8110, Z divided by D equals 0.5 plus the square root of 0.25 minus that K that I've just calculated divided by 0.9, and this equation, it doesn't say that directly in the code, but I was curious, so this format of the solution is the solution to a quad equation. So basically you get Z over D equals to 0.5 plus 0.25 minus 0.0731, that I calculated there, divided by 0.9. That is the same as 0.5 plus the square root of 0.25 minus 0.0812, which is equal to 0.5 plus square root of 0.1688. And that is equal to 0.5 plus 0.411. So Z over D equals 0.911. So Z equals 0.911, D equals 0.11911 times 302 millimeters. And that is equal to 275.12 millimeters. It's basically 275 millimeters. So now we can just find out easily the AS required. That is equal to moment divided by 0.9 Fy times Z. I found out that M was 60 kilonewton meters in the previous video. So AS required equals 60 times 10 to the power of 6 divided by 0.95 divided by 4 times 460 times 275. That's equal to 499.72 millimeters squared. Therefore, AS provided 3 times 201, 603 is greater than 499, so everything's okay. Therefore, the bars provided are okay. That section is capable of taking the moment of the design support moment, 60 kilonewton per meter. So that's part of itself. There's one more part of this question left, which I'll do in part 3. It's not covered in the exam question, and it will now be a separate video, but I was just wondering how the Z over D is calculated and what the depth of the neutral axis is. So it's just this equation here. I was wondering how they calculated it. So now I've done some further research and I've found out how this is calculated as per BS 18110. So I'll do a separate video on that. And I found out also obviously that according to BS 8110, Z is equal to X, which is the depth of the neutral axis, is just D divided by Z. D minus Z divided by 0.45, that's X, depth of the neutral axis. But it doesn't ask you for this in this question, so I'm just going to do that in a separate video. So that will be a bonus video on the theory behind these. I mean, I noticed as well in Eurocode 2 that the depth of neutral axis is 2.5 times d minus z. So there's a slightly little bit different, but I'll cover that in the next video. So the solution to this question was, the question for this one was, check whether the steel reinforcement provided as shown in the figure is sufficient to withstand maximum design support moment hogging, and it definitely passes because the AS required is 500 and the AS provided is 603, so it's okay. Depth of the lever arm as well is 0.911d, so that's reasonable. So that's it. If you want to see how I worked out the moments, I've done it. There's the bending moment envelope I worked out in the last video, and you want to see how I got the bending moment support reactions for this beam, then please look at the other videos. So please, hopefully you found this helpful. Please like the video and subscribe to the channel for more of this content. Thanks for watching.